Good day, everyone. Welcome to the second lecture of organic reaction mechanisms. And this video talk, I will talk about the mechanisms in acidic and basic media. So there are lots of examples. There are three examples that I will show you, and these are organic reactions that you see in textbooks of organic chemistry. But before we go through those three reactions, um, I'm I want to emphasize with you the correct way of writing mechanisms. Say, for example, I have here a species which is depicted as A, and it is a nucleophile. So if we are going to write uh, a Lewis structure for this species, for example, it is isoelectronic with a halogen atom or halogen ion, for example, assuming that it is isoelectronic. So I also have here an electrophile, which I will depict as E plus. There are ways to write arrow pushings. One way of writing arrow pushing is starting from the charge. This is the negative charge towards the electrophile, and the head of the arrow is directed towards the electrophile. And the other way of writing is starting from anywhere of these lone pairs. Just choose any of these lone pairs, and the arrow goes like this. So which one is true? The correct way of writing mechanism is the red arrow. Please bear in mind that the negative charge is just a formal charge. It has nothing to do with electronic, not electronic. It has nothing to do with electron flow, or yeah, because charge do not flow. In organic chemistry, we should always practice writing mechanisms from starting from a lone pair down to a positively charged species. So please do it a good Please make it a habit to start your arrow from a lone pair and not the formal charge. And also another correct way of writing a mechanism is by starting the arrow from a bond. For example, you have this CH bond here. As we all know that CH bonds are quite basic, and they have sp3. CH bonds are nucleophilic. So arrow pushing could also be represented in this manner. There are only two ways where you can represent arrow pushing in mechanism. That is starting from a lone pair or starting from a bond. That's it. Those are the only two ways of writing arrow pushings. So there are different ways of writing mechanisms as well as drawing intermediates in such mechanism. And it will depend on what condition that you are using or is given in the reaction. In a typical organic synthesis reaction, for example, you have you have your reaction and you have finished the reaction. And after finishing the reaction, you will tend to do like a reaction workup. For example, if you have uh, oxidizing agents, you will quench it with a reducing agent. And if you have acidic substances that you add in the reaction flask, you will have to neutralize it with a mild base. Or if you have a base that you have added in the reaction flask, you will neutralize it with a mild acid. And after that quenching and neutralization process, you will extract your crude compound, extract it, wash it, and dry it using a brine solution and sodium sulfate or magnesium sulfate, and you'll get the crude organic product. All the aqueous layers will be separated from the organic layer. And as you get the crude, organic product, which is of course dissolved in organic solvent, you will have to rotavap it to obtain the crude product that has no wherein there is no solvent at all. So that's the basic steps on doing organic synthesis. Now, in this case, when you see some organic reactions in textbooks of organic chemistry, it is highly assumed that these reactions have already undergone reaction workup, like quenching, quenching or reductive workup, um, neutralization using a mild base or mild acid, and extraction, then rotary evaporation, something like that. So a typical example of writing a mechanism under strong basic conditions is um, as saponification. This reaction that you see is called saponification. This is saponification, wherein you have an ester as a starting material and you react with a strong base, which is NaOH, underwater as a solvent, and you end up getting a carboxylic acid. And of course, an alcohol. Now, please do note that mechanism under strong base would be a different kind of mechanism under strong acid conditions. So in this step, you have an ester. So what happens next as the first step is that you have a strong base, NaOH, wherein a nucleophile called a hydroxyl ion will serve as the nucleophile. No, not hydroxyl ion, but hydroxide ion rather. So please bear in mind that when you do mechanisms, you should always write down or draw the lone pairs to account for the correct arrow pushings. So in this sense, you will end up having this kind of mechanism or arrow pushing, and do it like this. So you'll end up getting a tetrahedral intermediate here. Okay. Say, for example, the OH is depicted as red. Okay. That one. So this one should be red. Remember, make it a good habit to write the lone pairs. So this tetroxide ion should have lone pairs seen in it. So what happens next is that these lone pairs will tend to flow like this and will end up eliminating this methoxy group. This is OCH3. This is the methoxy group, and it will give you this carboxylic acid. But the question is, will the reaction stop here? No, it doesn't stop there. Remember that you have a highly unstable methoxy group in solution, okay? That is presumed to exist in solution. You have a methoxy. So what happens next is that you have an acidic proton here, okay? This H. What happens next is that this methoxy group, which I will show as blue, please don't forget to write the lone pairs. Okay. This is O, then lone pair, negative charge. This methoxy group will end up abstracting the proton, the acidic proton here. It's like this. And you'll end up getting an alcohol, which is methanol. Okay. This is methanol, and an acetate ion here. which is a negatively charged species. Now, what happens next is that water will act upon this process. So water now will participate, and this highly nucleophilic oxygen, or this highly nucleophilic acetate ion, will tend to abstract a proton from water, like this. Sorry, that. And this will give up the following compounds, the carboxylic acid and the methanol, which is here. Okay, so as a byproduct, you have a hydroxide ion here, and this hydroxide ion will react to another molecule of the ester to do the same process all over and over again. And as such time that the starting material has been consumed already, then that's the time that the reaction will stop. So this is just a cycle that takes place over and over again. As long as you have hydroxide ion in solution from water, and you have starting material left in solution. Okay, so this is the typical mechanism for base promoted saponification. Okay. Saponification actually is base promoted in this sense, and as you can see, as I write down the intermediates, including all the chemical species around, they all have negative charges. So this is a unique property of this mechanism under strong basic conditions. The species that you see in the mechanism are negatively charged. There are lots and lots of negatively charged species in the mechanism. But how about if the condition is strongly acidic? Just like, for example, in this reaction, wherein you have a carboxylic acid, and you end up getting an ester. This is a familiar reaction. This is what we call a Fischer esterification. Sorry. This is a esterification reaction, wherein you have an alcohol, you react it with a carboxylic acid in the presence of a strong acid. And typical example of a strong acid is sulfuric acid. So what's going to happen next? The first step, unlike the strong basic conditions, is that you make this carbon here, you make this carbon electrophilic. Then in this sense, actually in this kind of structure, this carbon, which I emphasize, is actually electrophilic. But during this process, it will be converted to an even more electrophilic carbon. And how do we do that? Well, sorry. Remember that you have a strong acid, which is H2SO4. For example, I write here the Lewis structure of H2SO4. Okay. So this is the Lewis structure, and the acid will act as a proton source. So what will happen next is that the lone pairs in this oxygen, in this sp2 oxygen, will abstract a proton from the sulfuric acid. Okay. And the product of the reaction of such process will be like this. A highly electrophilic species. You have OH here. Okay. And the next step, since you have a very electrophilic carbon here, The next step would be nucleophilic attack with methanol. OH, no, 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 no. This is methanol. I should write it in blue. So like this, this, okay. So that's how the mechanism looks like. So this process will give off this intermediate. So this should be positively charged because this is an osonium ion. Okay. Remember, take focus on this structure. You have a diol, where gem diol, particularly. This is a hydrate or gem diol. Remember that gem diols are unstable. Yeah, it's naturally unstable. And when you subject this kind of compound, when you have a compound, for example, this reaction, the crude product of this reaction, you subject it to, say, for example, negative ion mode ESI mass spec, mass spectrometry. You can see intensities of the gem diol, but not too much, but not too high intensity because they do not really exist for longer periods of time in your reaction. It will tend to decompose and it will really favor decomposition because of its instability. And what's going to happen next is that this, before decomposing, before the decomposition of this gem diol, is that remember that there is a bisulfate ion that will be formed during the first step because of this proton abstraction. So this H2SO4 will be converted into its conjugate base, which is a bisulfate. And this bisulfate ion here, if I will write the bisulfate in this form, sorry. Okay. Okay, this is the mechanism. Like it will abstract this proton and shifts this electrons towards oxygen because oxygen is positively charged. Okay. So this gonna give you a gem diol that looks like an acetal, a hemiacetal. This is a gem diol that looks like a hemiacetal. Okay. So this one is highly unstable. This is an unstable intermediate. So this will tend to decompose further. And how are we going to do that? Are we going to depict the mechanism? Well, simply by abstracting a proton again from the sulfuric acid, because during this process, the bisulfate will abstract this proton and will end up getting H2SO4, right? So during the course of this process, you have sulfuric acid back again. So the mechanism would be like either of these OH groups, either of these two, will tend to abstract a proton from sulfuric acid here, and thereby eliminating a bisulfate again in the reaction. And so you have, now you have a H2 plus. And you'll end up getting this positively charged intermediate. Okay, here. And what's gonna happen next is that this hydronium, oxonium ion here will become a leaving group, okay? Because basically OH is a strong base and leaving group ability is inversely proportional to base strength. When you have a strong base, you end up getting a poor leaving group. So that is why OH groups are poor leaving groups especially in substitution reactions. And in order to make it a better leaving group, you need to protonate it. So that is why this OH here, that is why this hydroxyl group was protonated from an acid. Sorry. Okay, that is why this OH was protonated to make it a better leaving group. And as a consequence, the mechanism would look like this one, and you'll end up getting another positively charged species, an oxonium ion. Another oxonium ion. This one. And this one, this is a positively charged, this is electron deficient oxygen. This H, remember that we have generated a bisulfate base here. So this bisulfate will tend to abstract this proton. Okay, the mechanism would look like this and this. Afterwards, you'll end up getting this product, this ester product, methyl ester, methyl acetate here, and water. This methyl acetate comes from this species here, this one, and this water comes from where? This one. Okay, so that's how you are going to write a plausible mechanism for reactions under strong acidic conditions. Okay. Did you see the difference? In strong basic conditions, the dominant species are negatively charged, but in strong acidic conditions, the dominant species that exist along the course of the mechanism are positively charged. That's the difference. So how about if we have organic reactions under weakly basic or weakly acidic conditions? So what could the mechanism be? Remember that we are using water in this reaction. You have an acid halide here. You have an acid halide, and you will hydrolyze it to produce a carboxylic acid or form a carboxylic acid and a byproduct, which is an acid as well. Okay. So the first step is like the mechanism that I've shown you on the strongly basic condition. Okay. You have water here, and this will attack the electrophilic carbon, and you'll end up getting a tetrahedral intermediate here. You have Cl, you have water, hydronium ion, plus. This is positively charged, this is negatively charged. Okay. Now what happens next is that These electrons will flow like this and will end up eliminating this chlorine atom, thereby giving you this species. Sorry. And remember, you have a chloride ion in solution. Okay, always depict it in proper Lewis structure, in the correct Lewis structure. So you will end up having like this chloride ion will abstract this proton, and mechanism looks like this. So you'll end up getting, and during the course of the reaction, the process, you'll end up getting HCl, this, which is actually this one. And this one is actually, when you deprotonate this moiety here, you'll end up getting the carboxylic acid as a product. So there's actually a crucial thing here. Like, it really makes confusion if you can really find the question, if you really have that question in mind. Okay, I will use here, and here. Why is it that the chlorine atom is the one that is being considered a leaving group and not the OH2 plus group? Even though the OH2 plus is positively charged, it needs electrons, but why is it that the chlorine atom is the one that gets eliminated? Now, to answer the question, we will go back to the fundamental principles of atomic size and atomic radius. So if this is a carbon, okay? You have a carbon chlorine bond and you have a carbon oxygen bond. Remember that the bond length, the longer the bond length, the weaker the bond strength. The longer the bond length, the weaker the bond strength. And why is that? If we are going to depict these atoms into an orbital description, for example, I have this as carbon, and I have this as oxygen, and I have here chlorine, which is a bigger atom than oxygen. It's carbon, carbon, and you have oxygen and chlorine. Remember that the bond length can be described by the distance between the nuclei of two atoms. So therefore, speaking of in that sense, in that kind of depiction or description, the carbon-chlorine bond will be longer than as compared to the carbon-oxygen bond, because that is the effect of atomic radius. Remember that there are electrons in the electron cloud of this carbon and also in this chlorine atom. If they draw closer or draw near to each other, they will get repelled. That is why they will tend to like get a little bit distant than compared to the carbon oxygen bond. And that is due to atomic size of the chlorine atom. And remember, the bond length is measured as the distance between two nuclei. That is why this bond right here between the carbon and chlorine bond is the longer bond, and it is the weaker bond. It has less bond strength because it is longer. That is why when you have electrons coming toward this carbon here, toward that carbon, the chlorine atom will tend to be eliminated first, because this bond between carbon and chlorine is a longer bond than the carbon-oxygen bond. That is why it gets easily eliminated. It has something to do with the size of the atom. And another factor which is less, which can be less explained or which is less reasonable, but it actually is insightful, okay, is the electronegativity. Remember that oxygen is more electronegative than chlorine. So remember that, always remember this in mind. Bear this in mind that, sorry, good living group are weak bases, okay? And if we compare, if for example, the conjugate base of the hydronium ion is in water and you have the conjugate acid, you have a chloride ion, for example, if we compare the pKa, the chloride ion will have like lower pKa than water, okay, than water. So therefore, having lower pKa, it is more acidic, and therefore it is weakly basic, okay? And being weakly basic in itself, it becomes a good living group because of less attraction towards the carbon in the tetrahedral intermediate as compared to this oxygen, which, and that will be supported by the fact that oxygen is more electron rich than the chlorine atom because it is more electronegative. It tends to gets easily attracted to the tetrahedral carbon center than the chlorine atom. It has something to do with electronegativity, but for me, the best explanation for that is the atomic size, because atomic size has an effect to the bond length and therefore the strength of the bond. It has something to do with atomic size. Okay, so this is the end of my lecture, online lecture for writing mechanisms under acidic or basic conditions or medium. Okay, so please stay tuned for more videos like this. And if I have time, feel free to hit like and subscribe to my channel, and I will upload more and more videos like this. Okay. And please keep yourselves posted about my new videos by subscribing to my channel. And thank you for listening and thank you for watching. I hope you have garnered a new learning from this